Okay, well, thanks all for coming. I'm going to talk about CLASSIX. You might have heard Shinje giving a talk about this about 1 year ago or so. This was part of his PhD. In the meantime, quite a few things have happened. So Mike Croucher got quite interested. Some of you know Mike. He's working for the MathWorks. And he actually took our Python code that we released last year and implemented it in MATLAB. It was an object-oriented code. And this is when I started actually really playing with this clustering algorithm, much more than we did when writing the paper. Part of the reason for that is that in MATLAB, we have this really excellent profiler, which we don't have in Python, right? I mean, I know there are ways to profile Python code, but it's just nowhere as convenient as profiling code in MATLAB. So I started playing with this code, and then I also noticed that the Python code can be improved. So using the MATLAB implementation and playing with that, we have since then sped up the Python implementation by a factor of 50 or so. And then we have gone back and improved Mike's MATLAB code using things that we have learned in Python and got yet another factor of 10 or so speed up on some of the large scale data sets that we have. So I think one part of the story here is that I found it very useful implementing the same algorithm in 2 different environments and basically improving both of the codes simultaneously. CLASSIX is a data clustering algorithm that promises to be fast, and I hope I will convince you, showing you a few live demos. It is memory efficient. CLASSIX memory consumption is linear in the number of data points. That is much different from other methods that, for example, use tree-based data structures. So it can scale quite nicely. It is a very simple algorithm. It's non-iterative. It's essentially a direct method which follows a few essential steps, and it's 100% deterministic. So there's no random initialization or something like that. When you run it, you get a result, and that will be the same on every run. It's relatively easy to tune. It has 2 main hyperparameters. Essentially, every clustering method will have some parameters because clustering is such a vague concept, right? If I give you, let's say, 20 data points, you could say, okay, I cluster them all in a single cluster with 20 data points. That's a valid clustering. Or you could come up with 20 clusters, each just having a single data point. And somewhere in between typically is where you find some practical application. So there needs to be at least one parameter that specifies the expected coarseness of the clusters you want to compute, and that will be heavily application dependent. So CLASSIX has one main hyperparameter that controls the coarseness of the clustering, and then another one to get rid of noisy clusters, so which are very small clusters. I will show you in a minute what this means. And CLASSIX is also fully explainable, which means it provides textual and visual explanations of the clusters that have been computed. And as I mentioned, there are currently 2 implementations available. So let's just, by the way, this is a MATLAB live script, which I've just started using recently. It's basically the equivalent of Jupyter Notebooks for MATLAB. It works quite nicely. So this little snippet here generates 2,000 data points in 2D space. And each of them corresponding to a sample of a 2D Gaussian, right? So we have 2 of these blobs here, and we want to cluster them. And yeah, visually looking at this, it seems reasonable that there should be 2 clusters. I mean, this is how this data has been generated. And if we want to cluster that, all we have to do is call the CLASSIX function, which takes as input the data matrix, which is a tall, skinny matrix. So it has 2 columns because we have 2-dimensional data here. We have 2,000 data points. So it's a 2,000 by 2 matrix. And here are the 2 parameters that are required. So the first one is the so-called radius parameter, which controls how coarse we want the clusters to be. And I have picked good parameters here. I mean, this requires a little bit of experimentation. And that's the case for any clustering algorithm. So just for some reason decided that 0.2 is a good parameter here. And then min PTS, this is a parameter that is typically easy to choose because it basically is the minimum number of points you would accept in a cluster. So if you don't want to end up with clusters that have just single points, you'll want to increase min PTS. And the way we recommend using the algorithm is as follows. You start with a rather large radius parameters because the larger you choose radius, the faster the method gets. So maybe radius 1. And you set min PTS to 1, which is the minimum value. You compute cluster, and you will get a certain number of clusters. If this number is too small, you will successively decrease the radius parameter until you hit approximately the number of expected clusters. And then you will increase the min PDS parameter until you got rid of all these tiny noisy clusters. So there's kind of a recipe for how you can tune these parameters interactively. So let's just run that. So this has basically now performed clustering. The output, there are 3 output parameters. The first one is just a vector of labels. So for each of the 2000 data points, we get a label, which is either 1 or 2 in this case. And then there's a function handle to the explain function. And then there are some other outputs that I'm not going to talk about. This explain function we can just call, and it will give us an overview of what happened internally in the algorithm. So it tells us that we cluster 2000 data points with 2 features. We have set certain parameters there. And then there is some auto scaling going on. So we want this algorithm to be shift and scaling invariant. Like if you take your point cloud and you shift it in space or you scale it, you certainly don't want the number of clusters to change. So we auto scale it by some factor, which is displayed here. And then we are grouping data points together. So this is the first stage of the clustering algorithm, which is an aggregation stage of data points into groups. And in this case, we have computed 93 groups. And when I explain you later how CLASSIX works, you will understand better what's going on here. And for the computation of these groups, we have done about 12,000 or 13,000 distance computations. Okay, so each data point has been involved in approximately 6.4 distance computations, which is a low number. Right? If you were to compute all the pairwise distances between these data points, it would be 2,000 squared. So that would be the number of distance computations that a brute force approach would require. However, we only required 6.4 distance computations. And then these 93 groups have been merged into 2 clusters. So the merging step is another phase of the algorithm. And then we get a picture of the result. So this is what came out of the algorithm. And the explainability feature, just to show you how this works, works as follows. You can call this explain function with input arguments. In particular, if you give it the indices of 2 data points, let's say 10 and 200, it will do the following. It will tell us that data point 10 was in group 4, whatever that means. Data point 200 was in group 27, and both of them have been merged into the same cluster number 1. And then it tells us that there is a path of data groups starting from group 4, which was the first data point, to group 27, which is the last one. And the step length between these groups is bounded by a scaled multiple of this radius parameter that we have chosen. So here's a picture of how this looks like. Data point 1 is the magenta cross here in the green circle. That was in group number 4. So the group circle is shown here. And data point with index 200 is in this circle here, the cyan circle, and it's this data point here. So these are the 2 data points. And you see here that there is a path of data points which are nearby. So a small step length that brings us from this data point to this one. Okay, so the explanation for why these 2 data points ended up in the same cluster is that you can go from one to the other in small step sizes without leaving the cluster. Okay, that's essentially how CLASSIX explains when 2 data points are in the same cluster. And of course, there's also an explanation for 2 data points not being in the same cluster. So if there is not a path of this type that would connect 2 data points, then they are in different clusters. So it's kind of a complete characterization for why 2 data points either ended up in the same cluster or not, in terms of paths within the cluster connecting these 2 data points. Okay, now the question is, of course, there are hundreds of different clustering methods. And how does it compare in practice when we actually work with some real data sets? We have a large number of demos in the GitHub repos. So there is one for the Python code and there's one for the MATLAB code. And I'm just going to pick out one of them, which we have just added recently. So this is a data set that has been provided by Roberto and Thomas, who are in our department. It's for one of their papers that is currently in review. They have downloaded RNA sequences of COVID viruses. Okay, so these are these string sequences of A, T, C, and G. Then they have taken these string sequences, and there were 5.7 million of them, and converted them to a numerical representation using so-called k-mer counts. So you're basically counting the frequency of triplets of letters appearing next to each other. K was equal 3 here. You get a high dimensional vector in the dimension of 1,000 or so. And then they have used a dimension reduction technique called PAC-MEC, which has reduced these 1,000 dimensional vectors down to 3 dimensions. And this is a data set that has 5.7 million data points in 3-dimensional space. And we have added this to the Python repository of CLASSIX. So it can be just loaded by calling the Python code, and then within that, the load data function. So this is, by the way, the rather new MATLAB Python interface. So you can easily interface with Python code from within MATLAB. And all you have to do is you just have to prepend your Python function with py. What comes out of this is a data frame, a pandas data frame. So we need to do a little bit more work to convert this data frame into a NumPy array first, and then from NumPy array to a MATLAB double data matrix. So this will now be a matrix of size 5.7 million by 3. And then we also know the ground truth labels. So there's another vector telling us exactly what the expected labels for this data would be. In the code that Roberto wrote for their paper, they also apply some data scaling. So they squeeze everything into the unit cube and then average it. So there's a bit of data scaling going on here, and we are just doing exactly the same scaling as they do in their paper. Okay, so this works quite efficiently. So this loaded the data. You can see it down here. It's now in memory. So here's our data matrix, and somewhere are the labels, the label vector. And we can now just work with this in MATLAB. So here is how we would, well, we have seen this before, right? So again, we choose some parameters. Radius 0.2 works again quite well here, and then min PTS has just been chosen as 500. So these are parameters that Roberto chose for their paper. And then I'm doing 2 other things here. So I'm using 2 functions that can score the quality of a clustering, so-called adjusted run score and adjusted mutual information. So these are kind of measures for the quality of a clustering when you know the ground truth labels. So for example, this adjusted run score is a number between 0 and 1, and it would be equal to 1 if you have 2 clusterings that perfectly coincide, and otherwise it would be lower than 1. And mutual information does something similar. So we can use this to get an idea of the clustering quality. So let's just cluster these 5.7 million data points. We are still in CLASSIX, so you can see here the live script tells us what line we are executing. And actually, a large portion of the execution time is spent on computing these scores, ARI and AMI. So we are now actually stuck in this computation. It seems to take longer than clustering the data. So this took about 8.5 seconds. In the previous one, it was 5 seconds, but I currently also have Zoom running in the background and the PDF viewer, so who knows what's going on. But it's small for 5.7 million data points. And the ARI score and AMI scores, they are apparently very satisfactory for this real-world data set. We can also call the Python implementation directly using the MATLAB interface. And it turns out that this will run approximately a factor of 2 slower. So the Python code, when called via this MATLAB Python interface, is about, or was about when I ran it before, a factor of 2 to 3 slower than the MATLAB implementation that we have. Just going to wait for that quickly.
Why is that, Stefan?
We don't know exactly. Yeah, but so Python uses NumPy, so it's probably some inefficiencies in NumPy. On the other hand, I must say that after all, I was kind of surprised because I was always thinking NumPy is very slow. A factor of 2 is not too bad, really. I would have expected this being much worse. But yeah, it's a factor of 2 roughly. It gives exactly the same numbers. The codes are identical. They should produce the same results. Yeah. I'm not going to run this in the interest of time, but I just want to show you quickly how you would do the same thing in Python. So in Python, in order to use CLASSIX in Python, you need to pip install. So pip install CLASSIX clustering, then just import CLASSIX, and then we can load the data using the load function. I'll leave this running in the background, but the syntax is very similar. And one thing I wanted to mention here is that this data set actually comes with some text labels. So these Python, these COVID viruses, they have some string identifier, HCOV-19, COVID-19, I suppose, and then there's typically the country this was tested for, and then each of them has some identifier, and this is supposedly the year the test was made, right? So these are just some labels that we have for the data. Now these labels, when you're working in Python, because we have data frames, we can call the CLASSIX explain function using data frame labels. So I can ask, so I get some clustering out of it. It's displayed here. So this is the clustering into 25 clusters of these 5.7 million RNA sequences. And the colors indicate to which cluster a data point belongs to. Just to remind you that this is actually three-dimensional data, which we are displaying here in 2D. So sometimes you might see data points that look very nearby, but actually in 3D space, they might be far apart. So there's some projection going on, right? So things might overlap, although in three-dimensional or higher dimensional space, they are not really overlapping. But then we can, for example, ask, why is this COVID virus that was tested in Denmark, why is this in the same cluster as the one that was apparently tested in Costa Rica? And I wouldn't claim that there's any deeper meaning to it, but we get an explanation here, right? So it tells us that you can go from the RNA that was in Costa Rica, you can go to the Denmark one using this path of RNA sequences. So via Switzerland, Hong Kong, and so on. Yeah, so yeah. All right, so let's go back to MATLAB. Yeah, just to show you an example. So this is the dbScan function that is within MATLAB. This calls a C code, so it's or C++. It's a highly optimized implementation of dbScan, and on my notebook at least, I can only run this on 15% of the data until I get an out of memory error. So I'm running it on 2% of the data in order to get a runtime which is less than a minute or so, and it gives similar quality clusters in the end. So if you remember from before, we had an ARI of 0.46 and AMI of 0.6. So these numbers are, the parameters here have been tuned so that the clustering is more or less the same as computed by both methods. dbScan produces a rather large number of noise clusters. So we had only 25 classes before, now we have 38, but these 13 additional classes, they have only a small number of data points. So this can be ignored and doesn't affect the overall clustering quality too much. We have tried to run this on our statistical compute server Minerva that we have. And these are measured runtimes on this data set as the number of data points increases. So this is CLASSIX, pretty much stays, well, it's not constant, of course, it grows mildly linearly. And this is dbScan. So it appears to be approximately a quadratic increase in computation time as the number of data point increases. And this goes up to 10,000 data points here. And then we have done some extrapolation that the whole data set would require approximately an hour. I have not actually run it for 1 hour. Maybe I should do that. But if you extrapolate this quadratic curve up to 5.7 million, you will end up with a runtime of 1 hour roughly for dbScan. Okay, so now maybe just a few words about how does this work. And as I mentioned before, it's a very simple, conceptually simple algorithm. So let's assume that our data is specified in form of a matrix with n columns and d rows. So d is the dimension of the data, n is the number of data points. And we make sure that we have empirical mean along each row of the data, right? So we take off the mean vector from each of the data points. Of course, this doesn't change at all the relative distance of the data. It's just shifting it around in space. And the trick is to sort the data points along their first principal axis. So if you imagine you have like an elongated point cloud in high dimensional space, the first principal axis would be the vector that points along the main direction of this data. So we sort along the first principal axis. It's actually not too important that it's necessarily the first principal axis, but the sorting is really key. And I will show you on the next slide why. The first principal axis turn out to be the left singular vectors of this data matrix. Because our data matrix has been mean-centered, you can get the principal axis just by computing the left singular vectors. And once we only need the first one actually. So U1 would be the first principal axis. And we just want to compute scores, so scalar values associated with each data point by projection onto the first principal axis. So these are the numbers alpha 1, alpha I that I call them here. And if you happen to have a full SVD or an economic SVD of your data matrix, you can just read them off from the first right singular vector. You get these essentially for free. And now the idea is to sort the data points according to these scalar sorting keys. So the most negative value would be alpha 1, and then we have them aligned in non-decreasing order. The cost for this is linear in the number of data points, because we're computing an SVD of a skinny matrix, assuming that the data dimension is small compared to the number of data points. And the sorting is really usually negligible, but I'm just writing here for completeness that you can do this in n log n operations. It's just sorting a long vector of scalar values. That's very quick. Now, because we have computed these alpha i's, we can use them to now prune the search space as we are computing pairwise distances between data points. So by the Cauchy-Schwarz inequality, we know that the distance of two data points, xi and xj, is lower bounded by the corresponding difference in the first principal values, call them alpha I and alpha j. And because we have sorted the data points in this non-decreasing fashion, we know that as soon as we encounter a data point xj for which alpha j minus alpha I is greater than epsilon, some tolerance, then we know that all the following data points, so the ones with indices greater than j, so all the xk's, must have a distance that is larger than epsilon away from xi. Okay, so this gives a natural pruning condition for the search of data points. And this is what we use to greedily aggregate all data points into groups. So here's the aggregation algorithm. We take our data points, we sort them so that they are in non-decreasing fashion along the first principal coordinate. We label all of them unassigned. That would be the first step. I think I have some pictures for that. So here, given these data points, 12 of them, this might be the first principal axis. And we sort the data points along that direction. So 1, 2, 3, 4, 5, and so on. Then we have a concept of the first data point, right? Because we have sorted them. So we take the first unassigned data point, which would be x1, and we group all data points together whose distance from x1 is less than epsilon. Okay, so we compute these distances. And again, we are increasing the coordinate of the points we are checking. So we start checking the distance between x1 and x2. Okay, smaller than epsilon. Let's include it in the first group. Then we check the distance between x1 and x3. Distance is larger than epsilon. It's not part of the first group, so let's skip it. We compute the distance between x1 and x4. This one is included. And then we might compute the distance between x1 and x5. And this might be, so alpha 5 minus alpha 1 might actually be larger than epsilon, which means we can stop here. We don't actually need to compute pairwise distances for all of these data points because of the sorting we have applied. Once the first group is finished, we move on to the next unassigned data point, which was x3. And we will not revisit any of the previously assigned data points. So the red data points, they stay red. Okay. Here, it's only data point x5 that happens to be a distance of epsilon or less than epsilon away from x3. So it becomes part of the second group and so on. Okay, we continue. So there's a third group coming up here and the fourth group. So after this, we have now ended up with 4 groups of data points. And within each group, we know that the distance between the first point in that group, which we refer to as the group center, right? This would be a group center, this would be a group center, and so on. We know that the distances are less than epsilon. And now the next step is to just merge these groups into clusters. So this is the second phase, which is group merging. So let's say we have these 5 groups here. In each of the groups, we have a special data point, which was the first one of that group, which we call the group center. So x1, x3, x6, and x10. And now we are only working on the group centers. We are not actually touching the original data points anymore. And we will group groups together, or we will merge groups together whose group centers are less than 1.5 times epsilon away from each other. You might ask, why is it 1.5? It has to be more than 1, because if this distance was just epsilon, they would have ended up in the same group already. So it doesn't make sense. It also has to be less than 2, because if the distance is larger than 2, then you would get group circles which are not overlapping anymore. So it has to be between 1 and 2. And yeah, we could have chosen square root of 2 or something like that. But yeah, we have just fixed 1.5, and we have never changed this parameter. So it's not really a parameter anymore. We just choose 1.5 here. And for the group merging, what is convenient is that these group centers, they are also sorted by first principle axis already, because the original data was. So we can, for checking this condition here, we can use exactly the same pruning using the Cauchy-Schwarz inequality as before. Right? So we can again decide that, okay, if this group center is not within 1.5 times epsilon radius of this one, I don't need to bother about group center 10 anymore. Can't be within that radius. So that's basically the whole algorithm. I have some pictures here, so I think we can skip that. It's pretty clear how the group merging works. So these two things combined, aggregation into groups and the merging, these are the key elements of CLASSIX. There are a few other refinements. So if after the merging of groups, we end up with clusters that have a small number of points, less than min PDS, we just assign them to the closest group. So they become part of the cluster of the closest group, basically. So they're just reassigned. I mentioned already that we do some data scaling and shifting to make the method shift and scaling invariant. And then we have implementations for the explain function. So the efficiency relies on being able to do the sorting efficiently, which is n log n operations. And all of this can be done in place. So we have a linear consumption of memory. There's nothing that requires lots of data copying or something like that. Now, the data sorting helps us in 2 ways. The first way is that when we do these pairwise distance computations, we are accessing data always in memory continuous blocks, because we have some natural sorting of the data points. Whenever we compute distances, we are accessing in memory continuous blocks. And also we hope that this sorting by the first principle component keeps the number of overall pairwise distance computations low, because hopefully the sorting has had the effect that nearby data points in high dimensional space are also nearby when projected onto the first principle component. So this was kind of the state of the MATLAB code that Mike sent us. And when I started playing with that code, I noticed that there's something really strange going on. So here is what I call quite a surprising inefficiency in up to now current MATLAB versions. Hopefully it will be addressed in future versions. But I had not really experienced that before, although I have definitely used that particular computation many, many times in some other contexts. So what is the problem? When we do the aggregation and the merging, we are very often, or we are just basically the whole computation consists of computing many distances between data points. So xy might be our current group center. Now we want to compute all the distances between xy plus 1 up to the largest index we would consider based on this termination criterion. So we end up computing lots of these distances in the Euclidean norm. And the naive implementation of how you might do this in MATLAB is to do something like this. So this is your data matrix. You take columns I plus 1 up to k. xi is the point xi, and you do vec norm, which gives you the column-wise norm of this matrix, and then you find all the indices for which this is less or equal to epsilon. Right? So this is the naive implementation. And then you have to correct for the fact that you only started at column I by adding I here. Right? This gives you the indices. This turns out to be very, very slow. What is already better is to do the following. You basically use the binomial theorem. So for the Euclidean norm, this Euclidean norm here can be the square of this Euclidean norm can be computed by taking the norm of xi plus the norm of the column you're looking at, and then you take off twice the inner product between the two vectors. So norm 2 here is just the squared 2 norm of each of the data points. This will give you the same result, and you also avoid computing the square roots that are involved in computing the 2 norm, right? So by just squaring that, you get rid of the square roots. So now, and you can make this even slightly more efficient by bringing norm 2i to the right-hand side of this inequality, because then you save, instead of doing this number of additions, you just have one addition on the right-hand side with the scalar value. So that's the best you could get. And what we have achieved now is that these distance computations are reduced to vector submatrix products. So vector times a submatrix of our large data matrix. And you would expect this to be efficient because MATLAB is column major, right? So extracting a submatrix column by column, that should be quick. So let's see if this is actually the case. So I have here a simple example where I do this vector times submatrix computation. My vector is just 1 by 1000, and my matrix has how many? 1 million columns here and 1000 rows, and I'm computing A times B. So not sure why this is now so slow, but might be a memory allocation thing. Okay, there we go. So let's just do this one more time. And I might already talk about what's happening next. So this is the full A times B. And this is A times B, but only using half of that matrix B. So I'm basically just taking half of it by using this sub-indexing of the columns. And you might already see this in the, I don't know why it's taking so long, but you see that doing this here is about a factor of 4 faster than doing this, although in terms of arithmetic operations, this only should require half the number of flops. That's really bad. Why is this happening? Well, the answer for that is that actually whenever you do something like this in MATLAB, it first creates a copy of the matrix B. And that kills all the performance, basically. And I have done this often, for example, in Krylov methods, when you implement your GMRES or something like this, right? You're always accessing the first, let's say, M columns of V, which is your big Krylov submatrix. Every time you do that, MATLAB creates a copy first and then does the matrix vector multiplication, which is absolutely unnecessary. So what we have done, and that's the only part that is not pure MATLAB in the current CLASSIX implementation, we have a simple max file which fixes this. So it's basically just calling dgem, but it simply adjusts the pointers to the beginning of the submatrix you want so that you're not creating any memory copies. So apart from this, the MATLAB implementation is about 100 lines of code, and we have a max routine to do vector times submatrix products efficiently. And by the way, NumPy doesn't do the same thing. NumPy is efficient. It doesn't create any copies when you're doing that. So this issue doesn't arise in Python. And hopefully this will be fixed in future MATLAB releases. With this max routine, we find that CLASSIX is sped up by a factor of 1 to 4. Sometimes it doesn't do much, but sometimes it's a factor of about 4. And then when we compare the MATLAB implementation using max to Python, then we usually have about a 1 to 2 factor in timing difference. So Python is a bit slower, but it's not too bad, really. Okay, I want to wrap up. I just want to show you a few benchmarks. So how do you actually convince people to use a clustering algorithm? Unfortunately, there's no other way than to run many, many benchmarks. And I was so glad to have Shinje because he's very patient. So he must have spent months on just doing computations and comparisons with other algorithms. So here's an example where we have 200,000 data points in 5 dimensions, Gaussian blobs, and there are 5 ground truth classes, and we are comparing to HDBScan. This is done in Python, by the way, QuickShift++, which is a clustering algorithm developed by a group at Google. And of course, k-means, like one of the best known algorithms. So k-means is perfect for this data sets because we have spherical clusters which are well separated in space. And indeed, k-means runs in 0.4 seconds. Of course, we give it the ground truth number of 5 clusters for that. CLASSIX takes slightly longer, 0.7 seconds. But I was very surprised to see that these methods basically completely fail. I mean, you don't want to wait 190 seconds to cluster 200,000 data points, but that's really what happens in practice. And why did doing these benchmarks take so long? Well, not just because of that. Also, for a fair comparison, you want to tune the hyperparameters of each of these methods so you get the best possible results, right? So it takes ages to come up with these comparisons. This is the COVID data set that I already demonstrated in MATLAB. So here we have seen that's in the order of seconds. HDB scan and quick shift, if they do not run out of memory, they require at least 1 or 2 hours to compute clusterings of comparable qualities. So the ARI and AMI scores are shown here. They are kind of comparable for HDB scan and quick shift. And of course, k-means doesn't work very well because these clusters are nowhere spherical. They are really not like spheres. So we get quite bad scores. Although the computation is fast, the quality is not good. We have some high dimensional data. So this is the phoneme data set from a machine learning benchmark collection. So it's 256 dimensional. Again, here CLASSIX performs okay, about 4 seconds. And in terms of clustering quality, when compared to k-means, it's slightly better. And we have one more here. And you can do fun things with clustering, right? Once you have these algorithms, you can, for example, cluster images. So this is trying to cluster facial images by representing these pictures as high dimensional vectors and then just applying a clustering algorithm. And again, we are kind of comparable, maybe a factor of 2 slower than k-means, but we are getting better AMIs at least. And so on. There are many, many benchmarks we've run. So we have also tests like this where we run pretty much any algorithm that is known to mankind on these kind of problems. And spectral clustering works very well, for example, on this shape benchmark test here. But in terms of computation time, it can be very, very slow. So if you look, these are the timings, 0.5 seconds, and CLASSIX doesn't require anything in the range of milliseconds in terms of computation time. So I really like spectral clustering because it has a nice, beautiful mathematical theory, but in terms of algorithmic performance, we found it rather slow. Yeah, you can also do things like image segmentation. So if you have an image, you can think of each pixel as a data point where you encode the location, so the XY coordinate as 2 features of your vector, and then the colors as 3 data point as a 3-dimensional vector appendant. So you're clustering 5-dimensional data, and hopefully in the end you get out some clustering of your image into segments. So it's called image segmentation, and yeah, you can do that. I don't know if this is probably not the state-of-the-art method you would use for that, but again, in terms of timings, we're doing very well compared to the other methods we have tried. Okay. So just to summarize, CLASSIX is a fast and explainable algorithm. The key steps were first to sort the data along their first principal axis. Then we had this kind of greedy aggregation of data points into groups using PCA to prune the search. Then we are merging groups into clusters. And then finally, if we end up with clusters which are tiny, we reassign them to larger clusters. It is very easy to implement. Maybe not easy to optimize because you have things like the behavior of MATLAB on submatrices, but essentially it's a few lines of MATLAB code, and it appears to be competitive with state-of-the-art clustering methods. And we are not really aware of other methods that offer the same level of explainability as well. So I think that might be a useful feature to have. And if you're interested in trying it out, you can just do pip install CLASSIX clustering, and we have a preprint on the archive. That's it. Thank you.